involved with setting up the modeling of the inversion of the magnetic field data from HMI from the very beginning, and played an instrumental role in all of the data that you've been looking at. And so now Rebecca's going to talk about magnetic field diagnostics. Thanks, right. Rebecca, go ahead.
Well. Yeah, slides are okay?
Yes.
All right, yeah, so I was asked to talk about magnetic field diagnostics in the photosphere and above, inside and outside of active regions, and that is a really broad topic. So I hope to give you a little, just a very superficial, broad stroke kind of sense of how we do magnetic field diagnostics in the photosphere and the chromosphere. And as you know, the polarization of light contains a wealth of information about the strength and the orientation of the magnetic field in the sun's atmosphere. And this is because these magnetic fields have the ability to generate and or modify the polarization in spectral lines through a variety of physical mechanisms, most notably the Zeeman and the Hahn effects. So I'm just going to give you a very, very superficial overview of the diagnostic abilities of these two effects. So the presence of a magnetic field in the sun's atmosphere breaks the degeneracy amongst the magnetic energy sublevels in an atomic system through something called the Zeeman effect, which you're probably all very familiar with. And this leads to emergent polarization signatures that can be interpreted in terms of the strength and the orientation of the magnetic field. Now, the Zeeman effect is proportional to the magnetic field strength. And this means that when the magnetic fields are very weak, the signals due to the Zeeman effect tend to vanish. They're very, very small and get swamped in the noise of the observations. So this can actually result in underestimating the strength of the magnetic field, particularly in quiet sun regions. Also, the Zeeman effect signals tend to cancel out when mixed magnetic polarities are present in the resolution element of your observation in your pixel. So again, this also leads to underestimating magnetic field strength. And again, it's a problem that is mostly affects quiet sun areas where the fields are weak and small scale. The Zeeman effect is conceptually straightforward and computationally affordable to model. And these signals due to the Zeeman effect tend to prevail in the photosphere of the sun and somewhat in the chromosphere of the sun. As you go to higher and higher layers in the sun's atmosphere, the magnetic fields become weaker, and so do the polarization signals due to the Zeeman effect. So the Hahn effect, on the other hand, and again, very superficially, is just the modification of scattering polarization signals due to the presence of a magnetic field. And the Hahn effect is typically sensitive to much, much weaker fields than the Zeeman effect is. So this opens a diagnostic window into the weak field regime. It also typically retains sensitivity when mixed magnetic polarities are present in the resolution element of your observation. So again, expanding that diagnostic window. However, it is conceptually very complex and computationally very demanding to model the Hahn effect in spectral lines. And the signals tend to prevail in the chromosphere and the corona of the sun, in higher layers of the sun's atmosphere typically. Now, you can see that both the Zeeman and the Hahn effects have a complementary diagnostic use in many, many ways. The way we obtain information about the magnetic field in the sun's atmosphere and other properties of the sun's atmosphere is through spectral line inversions. Spectral line inversions essentially perform an inverse mapping between the observables, this is the intensity and the polarization of light as a function of wavelength, and the physical state of the sun's atmosphere, temperature, density, magnetic field, you name it. But spectral line inversions are plagued with a host of issues, and a lot of them derive from the fact that they're nonlinear and non-unique. Nonlinear meaning that the sensitivity of the Stokes spectrum to a given physical quantity in the sun's atmosphere can be very large in some physical regimes and zero or very, very small in other physical regimes. And the non-uniqueness of the inversion problem refers to the fact that there's often more than one physical state that can result in the same intensity and polarization spectra. The quality of the inference of the magnetic field that we make through spectral line inversions depends on multiple factors. Of course, it depends on measurement errors such as photon noise or instrumental effects, problems in the data calibration procedures, uncertainties. Also, it depends on what I like to call your measuring type, which is what spectral line or lines you choose to do your observation, what spatial, temporal, and spectral resolution you're measuring your spectral lines with, etc. But lastly, and what I really want to get to today is it also depends on the modeling assumptions or the approximations underlying your interpretation of your observations. So let me get into this. So this is the outline for the rest of my talk, and I'll just be showcasing through a series of a tiny handful of works that I'm going to use as examples to showcase different magnetic field diagnostics made with different types of spectral line inversion codes. And the difference between these inversion codes is the physics, the complexity of the physics underlying the radiative transfer modeling. So I'll first start with the Milne-Eddinton approximation, which is the inversion code in the data pipelines of the HMI and the Hinode SP instruments. Then I'll move on to local thermodynamical equilibrium inversions for photospheric spectral lines. And then I'll talk a little bit about non-LTI inversions for spectral lines formed in the chromosphere of the sun. And then at the very end of the talk, I'll give you just a tiny glimpse in about what people are doing by applying machine learning techniques to the inversion problem lately. So first, the Milne-Eddinton approximation. Milne-Eddinton assumes that the physical parameters that describe the atmosphere of the sun are constant with height. So this means that when you apply Milne-Eddinton inversions, you cannot get information about the stratification of the atmosphere. You can't get information about gradients in your magnetic field or velocities. Also, this Milne-Eddinton approximation parameterizes the shape of the spectral line with a set of somewhat arbitrary parameters that do not bear any relationship to the thermodynamical properties of the atmosphere, which means that when you do Milne-Eddinton inversions, you cannot get information directly about the thermodynamics of the atmosphere, the temperature, the density, you name it. Also, the polarization in the Milne-Eddinton approximation is due to the Zeeman effect only, and it is typically only valid. You can only apply Milne-Eddinton inversions to photospheric spectral lines, with one notable exception, which is the chromospheric helium-1 multiplet at 10^30 angstroms. Of course, the advantages of using Milne-Eddinton is that it provides an analytical solution to the radiative transfer equation, which makes it easy and fast to compute. And this also makes for very robust spectral line inversions that are easily pipelineable. And then, of course, we wouldn't use it otherwise, but it does provide good information about the average vector magnetic field and line of sight velocities in the region of formation of the spectral line that you're interpreting. So now just a couple of examples of how people have applied Milne-Eddinton inversion to obtain really valuable information about the vector magnetic field in the photosphere and the chromosphere of the sun. And this was referred to, it should have made a reference to these papers, but in a series of papers almost a decade ago, Christoph Kukan, which was a grad student of mine at the time, and his collaborators used Milne-Eddinton inversions to interpret or to infer the magnetic field in active region filaments doing inversions of the helium-1 10^30 multiplet. This is the notable exception to the application only to photospheric lines, and it's because of the peculiar formation mechanism of the helium 10^30 multiplet. But with using Milne-Eddinton spectral line inversions, he was able to obtain the vector magnetic field along the filament and in the chromosphere around it. And with simultaneous measurements of a photospheric spectral line nearby, he was able to also obtain simultaneous information about the vector magnetic field in the photosphere. So with these two things, he was able to reconstruct the three-dimensional structure of the magnetic field in the filament and below it, which led to the conclusion that these observations were compatible with the flux rope structure along the filament. Now, in a much more recent paper, and this is a different example, another ex-student of mine, Annabelle Marine, was able to track the changes in the magnetic field vector as a function of time in the penumbra of a sunspot. And what she found in particular was that there was an excess oscillatory power in the inclination with respect to the local vertical of the magnetic field in the penumbra of sunspots. And that this excess oscillatory power was always concentrated in some like filamentary-like structures that were mostly concentrated on the side of the penumbra that faced the opposite magnetic polarity of the active region. So she speculated, she interpreted this as this excess oscillatory power coming from perturbations in the coronal loops connecting the two magnetic polarities of the active region that were propagating down into the photosphere, creating this excess power in the penumbra of the sunspot. By the way, these observations were obtained from the HMI vector magnetic field data products. So a more sophisticated approach to a Milne-Eddinton inversion is inversions based on the local thermodynamical equilibrium approximation. Now, this approximation is valid in the photosphere of the sun, where the density is high and collisions are very frequent, and the atomic populations are dominated by the relations of Saha and Boltzmann. Now, LTI inversions are only, for this reason, only valid for photospheric spectral lines, but they provide self-consistent information about thermodynamics in the photosphere. So when one does LTI inversions, they can obtain information about the temperature and other thermodynamic variables. They also provide information about the stratification of the thermodynamics and the magnetic field in the photosphere of the sun. So they're really valuable if one wants to get into this kind of detail. However, LTI inversions are more computationally demanding than Milne-Eddinton. They typically need to be applied on spectrally resolved data to obtain meaningful information, and they are less robust than a Milne-Eddinton and therefore less pipelinable. So one example amongst probably hundreds of thousands of how people have used LTI inversions to obtain information about the stratification of the properties in the photosphere. I chose another paper by my ex-student Annabelle Belen. She studied the structure, thermodynamic and magnetic structure in sunspot light bridges and compared the structure to the surroundings. And amongst her many findings, she was able to extract information about the stratification of the temperature and the magnetic field in sunspot light bridges. And she found that, not surprisingly, the temperature above light bridges decreases with height. But she also found that the magnetic field also decreases in strength and becomes more horizontal above the light bridge. This is in contrast with findings that other people made by studying light bridges, and showcases the necessity to really do these kind of studies carefully to better understand these features and the role in the decay process of sunspots and active regions.
Rebecca, you have about 2.5 minutes left.
Perfect, thank you. So unfortunately, one cannot apply this LTI approximation for interpreting chromospheric spectral lines. When one wants to model a spectral line formed in the chromosphere of the sun, one has to reckon with the fact that it's have to solve the radiative transfer in the full-blown non-LTE regime, and also that the polarization is often due to a combination of scattering processes and the Hanley and the Zeeman effects. This makes the forward modeling of chromospheric spectra really computationally demanding. The traditional way we do the inverse problem adds yet another layer of iterations to this already complex forward modeling, and it makes it computationally prohibitive. So one has to make a series of approximations to render the chromospheric inversion tractable. Even with these approximations, non-LTI inversions are still very computationally demanding. They typically have finicky initialization procedures. They're highly fine-tunable, often unstable. And one of the approximations that is always made is that the polarization is only due to the Zeeman effect. So no considerations to scattering polarization and the Hanley effects are made. This limits the usability of these non-LTI inversion codes for chromospheric lines to field strength regimes above a certain threshold, where now the polarization signatures need to be dominated by the Zeeman effect. Below this threshold, which is typically in the low hundreds of Gauss, scattering polarization and the Hanley effect tend to dominate the polarization signals. And again, these non-LTI inversion codes would not do a good job at retrieving information about the magnetic field. Of course, we need non-LTI inversions to obtain information about the thermodynamic and magnetic properties in the chromosphere. And eventually, I hope they will be routinely able to tap into the Hanley regime to diagnose the very weak fields in the chromosphere. So here are two examples quickly of how people have applied non-LTI inversions for chromospheric magnetic fields. Then the first one, Jaime de la Cruz and his collaborators studied the magnetic field in the chromosphere during umbral flashes, and they found that whilst the temperature in the shock front of the umbral flash could show an increase of about 1,000 Kelvin with respect to its surroundings, they found that the changes in the magnetic field during the umbral flash were negligible. In a even more recent paper, Visses and his collaborators studied the magnetic field vector in the photosphere and the chromosphere during a flaring event. And among other things, they found that they were able to measure shear in the orientation of the magnetic field from the photosphere to the chromosphere and signs of magnetic rearrangement during the flare. And lastly, just very briefly, machine learning techniques have been applied to the spectral line inversion problem for a long time now. Actually, the first papers that I've seen are from the early 2000s, but the field has really picked up recently, and there's a lot more going on nowadays. This is just a selection of two papers, two relatively recent papers where people have applied machine learning to spectral line inversions. They've, in both of these papers, they're different, but in both of them, they've designed and trained convolutional neural networks to do the inverse mapping from the Stokes spectra to the physical state of the sun's atmosphere. These two papers, one trained on synthetic data, the other one's trained on inverted observed data. And in both cases, the neural network is able to retrieve information about the stratification of the temperature and the magnetic field and other properties in the sun's atmosphere, in the sun's photosphere. So they were actually both of these papers were done on photospheric spectra. Once trained, the neural networks get a speed up of 10 to the 5 to 10 to the 6 times with respect to traditional inversions. So that's the greatest advantage of them. And they may actually be able to help with this chromospheric inverse problem, which is a lot more computationally demanding. Of course, the negative aspect of at least these neural networks is that the results that they obtain are limited within the physics of the training data set that they're trained on. So they can't really extrapolate in a meaningful way outside of these training data sets because they're not physically based. And I know there's pointers in new directions for physically informed neural networks, but this is really not my field of expertise. So I'm going to leave it here. And if you have any questions, they're welcome. Thank you.
Thank you, Rebecca. Very nice talk. Appreciate it. It's amazing we can learn anything at all. It seems very complicated, and yet here we are, and we can seem to see quite a bit, even with the data from HMI that has fairly low spectral resolution. We have one comment in the chat, which is from Tim Bastian. He says, "Nice talk. As observers move into measurements of chromospheric magnetic fields, how is the specific height of a given measurement robustly established?"
That's a very good question. And I do not think that it's yet robustly established. I mean, in radiative transfer, the only robust measure of height is the optical depth, but that does not map directly to height, to geometrical height. I think there is a chance that both two-dimensionally constrained inversions or MHD constrained inversions and machine learning kind of inversions will be able to give us in the future better constrained height information.
Okay, thank you. We have a comment from Katie Lecca, who suggests that we look at a paper by Higgins et al. This is one of the Solstice papers. You can see it on arXiv, but the AppJ is taking a while because they don't seem to be able to talk to each other very well on CNN-based reproduction of HMI pipeline that is showing quite promising results.
Yep, thank you.
Any other questions? Okay, well, then I think we're pretty close to being right on time, given that we started a couple minutes late due to all the introductory material. I think we're going to move now into chat